How spoken voice becomes a packet. I mean, really, how does that happen? How does the words that I speak into a telephone somehow get converted into ones and zeros that are sent across the network in the form of a packet? Well, that's what we're going to explore in this chapter. And it's going to be some really interesting information. And I use interesting a little loosely because this does get very technical. That's why you see a little medicine bottle on here. I sometimes call this is, forcing people to take their medicine, to understand the deep secrets of how voice gets coded or quantized into a packet. Now, for those of you that are using this information for nothing but real world. I mean, you're taking this, you're going straight into your job. You don't really care about certification at all. You just want to use this and put it into action. This might be one of those videos that you want to come back to at the end. The reason I say that is this is primarily certification material. For those of you that are going after the CCVP certification, you will need to know a lot of this information because this does get into the in-depths of how it all happens. So with that introduction being said, here's what we're going to talk about. The first thing we'll look at is voice encoding. I call it the 4 steps to making voice digital, a recipe, if you will, to making this happen. We'll then visit something known as the Nyquist theorem, who was developed by Dr. Nyquist himself, and that explains how voice can be synthesized into a digital format of ones and zeros, how that happens. And we'll explore something known as quantization. And you might already be going, ooh, this sounds like it's going to get ugly. Trust me, it's not going to be that bad. I'm going to take it at a pretty plain English sort of view and try and stay away from the deep mathematics behind it because it really is interesting if you look at it at that level. Finally, we'll look at compressing voice, and I think the most useful information, I should say applying to real world, is the compression techniques. How we can take all of these voice packets and squish them down using our various codecs and all the different compression mechanisms, and to take a lot less bandwidth than they do in the typical PSTN format. We'll look at how that happens and look at all the audio codecs. And I think, again, the most interesting is how they do that. And I think you'll be mesmerized when you see this. It amazed me when I found out how. It's like, man, there are some smart people out there. So here is the 4-step recipe on how to turn spoken analog waveform voice into the bits that travel across the network. The first thing is we don't have time or the desire, I guess you could say, to really get into how voice works and analog waveforms. But if you've ever recorded your voice using a program like SoundForge or anything, you'll notice that it comes up with this analog waveform that it generates to represent your voice. And there's pitch and signal and volume and all that kind of thing that go into this waveform. Well, if we want to take that analog waveform, and this is literally the words that come out of our mouth, and take it and turn it into bits that we can squeeze into a network packet, the first step of the 4-step recipe is to take as many samples of the analog signal as you can. So you see right here we have our candidate that's going to have its voice turned into a spoken digital packet. So this dog walks up and says, woof, into a telephone handset. Comes across here, we have the analog waveform, and you follow it along, it goes woof, and tails off there. The first thing is to sample it as many times as possible. And I mean a lot. You see it says many. I mean thousands of times every single second it will actually take a sample of that. Now, the second step is to calculate a number representing each sample, and this is also known as quantization. We follow this path all the way across, and using a scale that we'll explore deeper as we go further into this, there's a scale of numbers that each one of these little dashes, each one of these samples represent. So down here, maybe we have the number of 1 comma 3, and up here we have 1 comma 4 as it keeps going up this path, and we'll explore the scale as we go further. But we sample thousands of these numbers and then convert those numbers to binary. You know, we could actually stop right there. Voila. We have a binary number representing all these samples that we can put into a network packet and send across to the other side. Now, when the other side gets it, maybe that's a router. that receives it. It's going to take these samples, put them back onto the analog scale, fill in all the gaps between them, kind of drawing the line that meshes up all these samples, and then plays it out to a receiving analog handset. At that point, we can hear somebody talking through a network with their voice being digitized into packets and then returned to analog. Now, what we're going to get into in this video is getting even deeper into compressing that signal. And this is an optional but nearly mandatory characteristic to gain all the advantages of voice over IP. Is I mentioned that we take samples, but these samples, as we go across that analog waveform there, could be even more spread apart. Because human voice, although this isn't quite human, human voice has very similar characteristics that we can replicate. And when we look at all the compression methods, I think you'll be blown away with how that is done. We can actually use a cookbook, if you will. That's actually what a lot of the technical people call it. A human voice cookbook that can generate a lot of these signals without actually taking so many samples of all that analog waveform. That's how we compress the signal. In order to understand the quantization process, we have to pay tribute to our friend Dr. Nyquist, which is this very intelligent looking gentleman right here. He created a theorem that just about all digital and voice over IP systems use nowadays called the Nyquist theorem. It says, and this is Jeremy's paraphrase of it because it gets much more technical sounding than this. It says, if you sample a signal in regular intervals of at least twice the highest channel frequency, the samples will contain enough information to accurately reconstruct the signal. Now, I know even with my paraphrase, just reading that, I go, wow, I think my brain just melted right there. What that means is essentially you have these frequency ranges that all human voice fits between. First off, let's look at the important frequencies. The human ear can hear between 20 and 20,000 hertz, and that's just frequency. And for instance, dogs can hear above that. You know how dogs can hear frequencies that the human ear can't. That's why we have those whistles that make them kind of yelp and things like that. This is the range that the human ear can hear. Now, human speech, when I'm talking right now, when you talk, when you pick up a phone and call somebody, our range of frequency is between 200 and 9,000 hertz. So as you speak, the human speech synthesis goes between these ranges, or human speech frequencies. Now, a telephone, a normal telephone that you pick up and call your friends in across the PSTN, generates signals between 300 and 34,000 hertz. Even though our speech methods, our speech itself, can go above that, just about all human conversation fits between these frequency levels. And Nyquist came up and said, you know what? I feel comfortable expanding that and allowing it to generate between 300 and 4,000 hertz. So the Nyquist theorem even goes a little beyond what the standard telephone channel does and can generate frequencies that humans don't normally speak in. So with that in mind, let's take a look at how the theorem and the frequency ranges go together. Let me read the theorem again a little slowly, a little more slow this time, now that we've seen the frequencies. His theorem says, if you sample a signal in regular intervals of at least twice the highest channel frequency. Okay, stop right there. Let's put a little bar right between there. He's saying if you sample it twice the highest channel frequency, the highest channel frequency is all this stuff right here. You can see that the human ear, this is the highest channel frequency it can hear. Human speech goes to this. The Nyquist theorem, which is used to generate voice, you can see, I don't know if you can see it, but right down here, I got this picture from, it says AT&T. Because AT&T uses the Nyquist theorem when they generate your voice going across their networks. What they do is they take the highest frequency, read it again, at least twice the highest channel frequency, which with the Nyquist theorem is 4,000 hertz. If you use enough samples that go twice that, I keep saying this because you're going to see a formula pretty soon. It says the samples will then contain enough information to accurately reconstruct the original signal. The original pattern that you were speaking can be accurately reconstructed if you sample twice that highest frequency. Now, Nyquist said that 4,000 is the highest frequency you'll ever have to sample for a phone conversation, right here. So, using that theorem, the sample size will be 2 times 4,000, twice the highest frequency, which is 8,000. Thus, to accurately reconstruct a signal, we sample, holy cow, 8,000 times per second. Isn't that insane? That's exactly what happens. Every second of voice. Oh, there it goes. A second just passed. If we were sampling my voice, that second would have 8,000 samples that is used to accurately reconstruct that. Now you can see I have this woof coming in here and just follow it along. Woof. And kind of tails off here at the end. We go ahead and we take a sample, and I put each one of these little bars is 1/8,000th of a second, and I couldn't fit 8,000 in there. My hand got tired. So we sample that, all the way down into all these integer numbers. And then that scale right here is called voltage. A lot of times the sampling scale we'll use for voice over IP is called pulse amplitude modulation, or PAM. It's a number scale that goes all the way up here that dictates an integer value for each one of these sample sizes. So you can kind of, let me grab a red color here so I can have a little different color. So I grab this right here, that's one sample. Maybe that's assigned value, 1. Up here, 2. Now, it doesn't use simple integers like this, but 3, 4, 5, 6, 7, 8, 9, 10, down, 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 and all we go. So it goes positive and negative, all these different integer values of pulse amplitude modulation. Once it's received at the other side, it takes all these integer values and redraws that line that is known as the analog signal form. Now, if we take 8,000 samples per second, that actually comes down to sampling once every 125 microseconds. Not milliseconds, microseconds. This is a fraction, a thousandth of a millisecond. So you can see that we're sampling a ton. So here's an interesting fact for you. If we look at this formula right here, we have the sample size is 2 times 4,000 hertz, and that equals 8,000. We put that down here. 2 times 4,000 equals 8,000 samples every second. And if we take that and multiply it by the fact that every sample needs 8 bits to create it. It uses just a standard byte of information, so 8 bits right there. You can do that math in your head. 0, 0, 0 equals 64,000. That actually comes out to, I get my 0 looking a little better, 64,000 bits for every second, because we're sampling 8,000 times a second. That sounds interesting, because we just happen to have a codec. Its name is G.711, which you guys have heard about plenty already, that happens to have a bandwidth consumption of 64 kilobits per second, or 64,000 bits per second. You also may be used to buying a T1 line, and you say, oh yeah, with that T1 line, we can end up getting 24 voice calls across, because each of those T1 lines has 24 DS0s. And how much bandwidth is in a DS0? 64 kilobits per second. It's amazing. All of the math works out. Now, don't sit there and think of it too long, or else it'll all slip away, because it does for me. If I sit there and start staring at this formula, how did that all work? Now, the reason G.711 is called a codec. A coder-decoder is what that stands for. It's called a codec is because they modified this PAM scale to have a lot more. You can see that I have these lines real close up here and then spread out at the end. Now, it's not only because my hand got tired drawing those, it's also because that is somewhat accurately of how G.711 works. It has closer sampling intervals right here, or closer as the range of hertz. Remember, this is a scale of hertz between 0 and 4,000, or 4 kilohertz, that it goes up. It samples closer down here because that's more of what normal human voice conversation is. If you had somebody always talking at the real fringe up here, 4,000, you'd really probably get annoyed talking and hearing that person because our ears are used to hearing most of our stuff in this range. You can see that, I have woof right here. This is a pretty high-pitched bark. Woof! It's a Lhasa Apso barking or something like that because it's going on this fringe range. And the further and further you get away using that G711 codec, the less and less accurate those sampling sizes are because they spread out the numbers more and more. So they're making a bet, and it's an accurate bet, that most human conversations will look more like, a scale like that, somewhere going down between the more moderate ranges of 0 to, say, 2,000 hertz or so. There are two forms of G.711. U-law coding, and my W's falling off here. I'm running out of space on my one slide, and A-law. Here's the way I remember this. U-law is used in the United States of America and Japan. I don't know how to squeeze that one in there. A-law is used in another place. So U-law is the coding we use here. A-law is another place, and they are essentially the same thing. They just use slightly different PAM numbers when they're encoding those, but they can accurately encode it voice the same way. So when you are selecting your codec on the router, if you're using a router that only is making calls to things within the United States and Japan, that is going to be all U-law. If we're communicating somewhere else, another place, that is going to be set up on the router as an A-law coding. Now, both G711 flavors fall under the umbrella of waveform algorithm quantization techniques. And what that means is that they encode everything that there is to encode about the speech pattern. We discovered that G711, which by the way uses a system called pulse code modulation, G711 sits there and it will take voice samples. Now, ignore the numbers. For instance, the range of values for voltage is just a generic quantization graph that I pulled off the internet, but it works well for an example. G711 takes 8,000 samples a second. We already saw that. So up here, it will go ahead and grab a sample of voice. We'll say, okay, the integer value of that is, we'll say, 20. It says 2, 0, but we're ignoring those values. So it comes out to 20. So it encodes that in binary, sends it. Right here, it comes out to maybe 16, codes that in binary, and sends it. Down here, it ends up being, we'll say, a 0 and so on, codes that and sends it. So every single voice pattern is coded and sent, which means that they can be pretty bandwidth heavy. They do use some predictive methods, and we'll see when we discuss all the specifics about waveform algorithms on the next slide. We'll see how they can predict what's coming, but overall, these are typically very bandwidth heavy. They don't use any dictionary of speech or anything like that. And I know this is the first time I've said dictionary, so you would think, how would it? Well, when you come down here to these source algorithms, these are commonly called voice coders, or slang is vocoders, just like I write right here. Vocoders. And what the source algorithm does is it encodes the changes between the codec. For example, right here we had a 20 and it will go ahead and code that, send it, just like G711. But for the next one, it will just say, oh, the change was a -4. It went down to this marking. Go ahead and send that. The change right here is a -16. Go ahead and send that. Now, it may sound like semantics, based on what it's recording, but using some of the advanced techniques that source algorithms use, they can actually skip sending a lot of this information that goes between there, which means you can get a lot of bandwidth savings with some of the advanced characteristics of source algorithms. And matter of fact, let's look deeper into each one of these right now. Let's start off by focusing in on the waveform codecs. There's really two of them that our Cisco routers use that waveform style of coding. The first one we've already seen, G711, uses pulse code modulation and chomps up 64 kilobits per second. It's one of the heaviest codecs that are out there because it literally codes each and every sample into its own binary calculation and sends it along its way. I showed you how the math comes out to get that calculation. Now, G726 is a new one for us. It uses AD pulse code modulation and eats up 32 kilobits per second, or 24 kilobits per second, or 16 kilobits per second. And I asked the question, well, what's the difference? How come this has, first off, 3 different flavors, and how come even the heaviest flavor is half of what G711 uses? Well, the reason why is I wrote right here, AD stands for adaptive differential. What that means is that this focuses in on some of the changes between the codecs. Now, I know that sounds like it's bleeding into some of those source codecs, the other major umbrella, and it is in a way, but this really still uses a lot of the original coding. Let me go back to that graph and show you. Here's how it works. Let's go back to our voltage and time graph right here. G726 will allow you to grab, first off, that initial voice sample. 20 is the number we said it came out to. Now, G711 uses 8 bits for every single one of these. So the next number right here, we said that was 16. We'll go ahead and use all 8 bits and send the number 16. Well, with the G726 codec, what happens is it will take 4 bits of the new and 4 bits of the old and combine them together to get that 8-bit sample. Now, I know it sounds a little weird, but here's the concept. The human voice patterns are very predictable in the sense that if you're taking 8,000 samples of a second, or 8,000 samples per second, you can pretty much bet that sample number 4,263 will be very similar to 4,264, right? I mean, think of it. How much can you say in a second? I say the word cow, and that takes a second, but inside of there I have k, 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 ah, 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 ooh, ooh, ooh. I know it sounds goofy, but really, if you really divided that up into 8,000 slices, just about every slice would sound nearly identical if played next to each other. I couldn't tell the difference anyway. So what G726 does is it says, okay, 20 in binary comes out to, 0, 0, 0. I'm trying to do it off the top of my head. 128, 64, 32, 16, 8, 4, 2, 1, right? Oh, I put an extra 0 in there. Well, you get the idea, right? We convert it to a binary number. 16 comes out to da-da-da-da-da, a binary number. So what it will do is it will take 4 bits of this 20 and combine it with the 4 bits of the new sample, or a 4-bit version of the new sample that it does, to get the 8 bits, since just about all the time these are going to be the same. So we go back to our G.726 slide, and we see that there's 3 flavors of G726. Here's the concept. This one uses half the bandwidth of G711 because it takes 4 new bits and combines them with 4 bits from the sample before to get the 8 bits that it needs to form a new sample. The 24 kilobit per second version gets 3 new bits and reuses 5 of the old. So that gives us the 8 bits that we need to form the new sample. 16 kilobit per second version uses 2 new bits and combines it with 6 of the old bits to get the sample that we need. Now I know if we think of this in pure binary, it makes no sense. We're kind of like, well, if you combine weird bits together, it's going to give you the wrong number or the wrong sample. But try not to think of it in terms of straight up binary, because getting the wrong number is obvious. What it's doing is it's really doing it in forms of a wave, a smooth analog signal. This one just grabs 2 new bits, this grabs 3 new bits, this grabs 4. So what do you think you're sacrificing by moving down to a 16 kilobit per second version? You got it. It's accuracy. Accuracy is what you're starting to lose because you're only using 2 bits of every new sample, but at the same time you save bandwidth. And this gets us to the game of bandwidth conservation with voice over IP, that it's going to take a lot of testing and a lot of trial to find out how much quality can I sacrifice versus how much bandwidth can I save. It's just a game of a scale that we'll have to play, and it'll really take a lot of testings to get you what you're comfortable with. Frankly, I've heard the 3 versions of 726, and I can't tell much difference. Now, other people can. In other countries where the language spoken doesn't exactly match a lot of the human speech characteristics, at that time, I'm not trying to make other countries sound like aliens or something like that, but there's different languages that need more change when they're communicating versus one of the smooth romance languages that a lot of our common languages fall into. So based on the language spoken and how much we can get away with, that's really where these 3 different versions come in. Now, G711 and G726 are the waveform codecs. They have nothing to do with these source codecs that use a totally different coding fashion. Now, I mentioned before that waveforms typically encode everything, and that's still pretty much true for G726. It's coding everything, it's just taking part of everything and combining it with an old everything, if that makes sense. With these source codecs, they encode the change, but this is where my wizard steps onto the screen. I'm not talking a wizard like next, 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 finish. I'm talking about magic. Pure magic is what I start getting into when I think of these G728 and G729 codecs. Here's what differentiates them. First off, you look at the bandwidth, and man, 16 kilobits per second, that was the low end of our waveform. And then you drop down here and it's kind of like, ooh, 8 kilobits per second. You can code a complete voice stream down to 8 kilobits per second? And the answer is yes. You can squeeze a voice stream across a 28 kilobit per second connection, and it works just fine if you're using this codec. So how's it do it? Well, G728 and 729 use very similar systems. Rather than coding exactly what the sample is, they will use the change and use something known as a human voice cookbook or codebook. And what this is a built-in dictionary that these codecs have that is engineered to predict the human voice. Now you see why I have this little wizard guy step onto the screen? I'm kind of, every time I even talk about this, I'm just like, wow, what does that mean? It means that somebody has engineered a dictionary, built them into these codecs, that it can actually predict what noise you are going to make as a human being next. So here's the concept. We take that little, waveform algorithm, take a human voice wave, I guess the dog wouldn't work for this one, but say a human voice says, woof. That pattern that I just said, and that pattern that I followed when I said that pattern, is something known as the human language pattern. They've studied it enough that they were able to create a dictionary that allows these protocols to look ahead. For example, let's focus on the word word. Okay. If I were to splice that up into 8,000 samples, I can say word in about a second, right? Word. If I were to splice that up into 8,000 samples, there's a dictionary built into these guys that allows them to predict what samples are going to send next. And instead of actually sending the sample, they'll use a mathematical recipe to synthesize your voice, but it still sounds like your voice. I mean, when I think of mathematical recipes to synthesize my voice, I think of, you've heard computers talk. Hello, thank you for calling. How are you today? I mean, that's what I think of synthesized voice. But it can take just a few samples of what I'm saying and synthesize it using these mathematical recipes, and it still sounds like me. That's the weirdness. That's the wizard behind all of this, is that it figures out a way to make it sound like you, inflection included. I mean, my inflection jumps from way up here to way down here, and it still can predict what's happening because it takes so many samples, and this mathematical algorithm is written for it. Now, the difference is, you can see G728 is 16 kilobits per second. It looks ahead of what I'm saying about 2.5 milliseconds and generates a lot of that using mathematical recipes. G729 looks ahead 5 milliseconds. And by the way, do you know Cisco's preferred #1 codec that they use for compressed voice? It's this guy right here, G729 at 8 kilobits per second. Now the beauty is they even enhanced it a little bit more. The original G729 was very hard on your processor. I mean, I guess why wouldn't it be? It's having to look ahead, synthesize, run mathematical algorithms thousands of times every second to generate your voice that sounds like you. Of course that's going to be hard on your processor. So they released G729 Annex A. And G729 Annex A allows it to be easier on your processor, meaning you can get a lot more bang for your buck if you buy some digital signal processor resources, which are just little processors that help code voice. You can get a lot more sessions with G729A than you could with the G729. But, of course, with everything like that comes some sacrifice. This is just a little lower quality than the original G729. Quality meaning how good the voice sounds. Now, I've heard G729A, and to me, again, I can't tell a difference. The only time I can tell a difference on these codecs is if you ever hold them up to a radio. If you're talking to somebody and they have music playing in the background, or they just stick the handset up to a radio, it starts sounding like junk. The music sounds real thin. Sometimes it just starts going when it's playing the music. And the reason why is this code book, this mathematical recipe, is not geared for a saxophone. It's geared for the human voice. So that's one of the things that you'll have to start to think about when you think about things like music on hold. Music on hold is just about everywhere for every company. When they put you on hold, it plays some music. Well, if you use G729 or 728 to stream that music, it's going to sound pretty bad because, again, it's coded for the human voice. So do you see why this wizard has walked onto the scene? To me, I get so excited when I talk about this because I'm just like, that's amazing. It's simply amazing. And that's all I can say about those codecs. And before we wrap things up, I have to answer the question I'm sure a lot of you are thinking, how good do these codecs sound? Is there any scale that we can use to say, this sounds this good or this sounds this good? Well, actually, there's many scales. One of the most popular is something known as the mean opinion score. What this is, it's kind of a funny test. They take a bunch of people into a room, have them put on a headset or listen to a telephone handset, and they'll say some nonsensical sentence, something that people couldn't predict you saying. Because, for instance, humans also predict each other. I unfortunately do it all the time with my wife. When I come home and she starts talking, I try and finish her sentences. It drives her nuts. So in that sense, you don't want somebody to be able to finish the sentence and then say, oh, well, I understood that just perfectly. Instead, they'll read something that makes no sense at all. They'll say, the red chicken flew over the water at night when it was red. And you kind of think, well, that made no sense, but that's the whole point of it. People will then listen to that and rate it on a scale of 1 to 5. 5 being fantastic, imperceivable, there's no problems. A 1 being horrible, I could barely, at a 1 that you can't understand it, is essentially the scale. Toll quality voice is rated at 4.0, and toll quality being when you're communicating with somebody off across the normal phone network. And you might say, well, why isn't it a 5? Well, if you have people listening for problems, of course, nobody's going to say, oh, it was perfect, because it can always get better, right? So toll quality is right around a 4.0 mean opinion score. Here's a list, and I pulled it right off Cisco's website. That's why it's kind of sliced off on the end here. This is a list of all the major codecs that Cisco uses on their routers, how much bandwidth they consume, the mean opinion score, and then it's sliced off over here. This is compression delay. That last word over there is delay. Let me talk about this because this has huge ramifications with what codec you choose. You can see right here, G711 pulse code modulation, bitrate of 64, has a mean opinion score of 4.1. People actually rate this as better than PSTN quality, and it should be for the pain it goes through to code that voice synthesis. Has very, very low compression delay. It can do it very quickly because all it's doing is taking samples and sending it. Very low processor overhead. Doesn't really have to do much at all. As you go down, let's jump to the first major compressed codec, G729. Look at that, bit rate of 8 kilobits per second. Amazing. Mean opinion score of 3.92, which is phenomenal when you consider that toll quality is 4.0. This is just barely underneath toll quality. Again, I've heard it many times. In my opinion, you can't tell the difference. However, you start seeing the compression delay start to go up. Now, if you've gone through the quality of service course, you know that voice has an end-to-end one-way delay of 150 milliseconds. Okay, so this takes 10 milliseconds to code that in. These are all in terms of milliseconds. So if it's taking 10 to code in and 10 to uncode on the other side, you've added 20 to your overall budget. So you subtract that out, you've got 130 left to play with. Now you have to cross the ocean, the distance you're planning on sending it. You also have to talk about serialization delay, which is how long it takes to put it on the wire. I mean, you run into a bunch of factors. So this is one of the major things. When you choose your codec, you're really affecting how long it takes to get from point A to point B. So you see, first off, G711 is pretty phenomenal when you compare it to all the other codecs. That's why Cisco uses it as one of their major codecs, the chosen codec, if you will, for all their IP phones. But you also notice if you have times 2 encodings, times 3 encodings, look at the quality drop. It's like wham, it's like it got taken out at the knees. Wham, it's down on the ground. It sounds horrible. This happens when you implement a feature known as transcoding. I'll just put trans. Transcoding allows you to compress and uncompress a codec as it crosses different networks. For example, you might compress it initially from G711 to G729 as you send it across the WAN, and then uncompressing it, at the other side to talk to a voicemail server that can't support anything. Well, once you're doing that, you're doing a double encoding, and it's like a copy machine. When you make a copy of a copy of a copy of a copy, your quality drops significantly. And the same thing happens for voice. Now, I have it shown right here with G729, but it happens to any of these codecs. If you convert and you change them all the time using transcoding, it's okay to compress and uncompress once. That's one encoding. But if you do it twice or 3 times, you see some major impact. And plus, every time you do that, you're adding 10 more 10 more milliseconds to your delay. Now, drop down here real quick. Oh, by the way, this is G729A. Notice that's the one that's easier on your processor, and it does take a little quality hit from the original G729 up there. So if you have processor resources to spare, G729A is probably something you want to hold off on. You want to keep with G729 because it's better quality. It just takes more processing power. By the way, while I'm talking about Annex A, there's also G729 Annex B you might have heard of. That indicates, or I should say, adds a feature called VAD, Voice Activity Detection. You may have heard of the old Simon and Garfunkel song, Listen to the Sound of Silence. One of my all-time favorites. Well, the sound of silence is officially coined VAD. That means when you're talking on a phone, there's moments of silence. For example, I might be talking and then have to think, oh, what was I thinking? Oh, and then I start talking again. VAD allows it to detect the sound of silence and stop sending bandwidth. Did you know, this is a wild statistic, but they have found through extensive studies that 40% of your phone conversation is actually silence. Isn't that wild? I mean, you think about talking, and it's just kind of like, wow, 40%, that's almost half of everything you do is just silence. So this is a major thing because if you're going by the average, obviously it wouldn't be me talking because I talk way too much. If you're going with the average, turning on Annex B can help you save 40% of your overall bandwidth. Now, Annex B doesn't have to be partnered with A. It's a separate annex. I could turn on G729B without turning on A, and likewise, I could turn on G729AB, which turns on both of those features. Finally, I want to talk about G723. When Cisco got into the voice over IP market, they did so just like every major company does by buying somebody else. They actually bought a company called Celsius, spelled with an S, Celsius. And Celsius used G723 as their preferred voice codec. And if you look at the quality and the bandwidth, this is an equally amazing codec. You notice it even uses a different waveform standard we haven't even talked about. And it uses 6.3 kilobits per second, which even beats out G729. Amazing. The reason Cisco ditched it, by the way, all first generation Cisco phones use this, and they were the ugly ones, the 12 SP Plus and the 30 VIP, no longer in production. They ditched that because of that one right there. Wow, major compression delay to code that stream of audio. You got 3 times the savings by going with G729 for just a small amount of bandwidth sacrifice. And you notice the quality on G729 is just about the same. It's slightly more than G723. The main reason was the compression delay and how much processor resources that took. So I have a feeling by this point, you are either completely amazed with your socks blown off or totally confused or some kind of combination of both, because that's most of what I do when I start getting into the intricacies of how spoken voice becomes a packet. Essentially, I hope you got the overview of this. Of course, not getting into all the mathematical algorithms, you can feel free to look on the internet. There is a ton about the Nyquist theorem and how it really gets in depth and converts all those. It's really interesting reading if you're looking to fall asleep. So you have right here voice encoding. Analog to digital. The first thing that we talked about, I talked about the 4-step recipe it goes through by taking the samples, using one of the wave coding techniques, converting it to binary, and then possibly compressing it. We looked at the famous Nyquist theorem, which has been around for many moons, on how to take analog spoken voice and convert it to digital. And when you say it that way, you realize just how long that's been around because just about every single PBX system does that. We went through the quantization techniques and, well, first off, understanding quantization as a whole, what that does, and then the different techniques used by the different codecs. We then turned into the compression of voice using those strange human voice dictionaries that allow it to smush voice down by predicting what you're going to say next. Again, wizardry is happening, strange and unusual things, but that's what those compressed codecs are all about, is smushing down your voice and saving a huge amount of bandwidth with not much quality degradation. I hope this has been informative for you, and I'd like to thank you for viewing.